I am delighted to welcome Professor Euisik Yoon here to the podium to enlighten us about how we go about talking to the brain. So, Euisik.
Thank you, Dennis. Thank you for a nice and kind introduction. And I feel really honored to name after William G. Dow. And probably the work that I do, if it has a little bit flavor of his research and activities, would be kind of interdisciplinary in nature. So in this talk, I'm going to covering my work in microprocesses and nanotechnology and optoelectronic devices and integrated circuit and system integration by interface, especially neurointerface or brain interface, electrically and also optically. So we're talking to the brain. Everyone does that every day, and probably verbally through the language, and also we communicate with others with a gesture and probably facial expression. And also I'm talking to my brain, also asking questions to myself. And also, I do not intend to get into the philosophical question, who am I? And the brain is actually myself, and how do we talk to each other? But as an electrical engineer, what I wanted to talk to the brain is and tapping into the neurons directly, not through verbal sound wave or any other gestures and optical images. So this is a brief history of a neural interface technology. This is a very biased view, mostly electrophysiology, meaning that how do we communicate with the brain electrically? About 100 years ago, Hans Berger, shown here, 1924, he's a physician, not a physicist. He tried to put an electrode in his son's scalp and tried to correlate electromagnetic wave with the brain activities. And some people say that we are lucky because he's a physician, not a physicist. Otherwise, he would not attempt to do this very absurd and crazy the trials. That is the beginning of the EEG, and still is being used in clinical applications. But this has a real limitation and spatial temporal limitation because it's only accessing the ensemble of large number of neural activities. It is like we put the microphone outside the stadium, try to figure out what's going on inside the stadium. And people try to get into the brain much closer by putting this ECOG and showing here that requires craniotomy, which is open skull surgery, place the electrode on the top of the cortex. Still, it's being practiced in clinics to identify the location of the focal seizure, and doctors are removing that spot of the brain and then close. But still, we put the microphone inside the stadium, but we are not hearing each individual person's voice. So next one is we want to put the microphone to each individual person. So that's what's happening in this, and single neuron activities, and then after having this, action potential has been discovered, which is a single neuron activity electrically. We can put a microelectrode here inside the brain, which means the implant and insert the wires, which is around 30 microns. There are many different forms of these wires, either tungsten or carbon, but place them close to the individual neurons. The problem is, it's very difficult to scale. Only one wire can record one neurons. So how can you monitor many, many neurons? So that's the beginning of this, and then late 1960s over here, and there's one first trial to utilizing silicon microfabrication technology to scaling this microelectrode. This is the first silicon probes, and it's done by Ken Wise, at the time was at Stanford University. This one is chiseling and machining the silicon into the very small needle, like in your hair, like 100 microns, and integrating the electrode on top of this silicon structure. That's the beginning of the first silicon probes, and Ken came in here in Michigan, and he started a program. And later, this is a seminal paper work was published. It's Khalil Najafian Wise, and Khalil has been EC department chair for 10 years and two terms. And then this actually including many electrodes onto the same silicon structure. And this signal is so small, then it's been amplified and digitized by circuit in the back. This is the first on-chip circuitry silicon probes. And after that, there is an evolution of the Michigan probes, and this name is not put by us, but put by the community, and community acknowledge this kind of approach as the Michigan probes. So there are many evolution of the Michigan probe technology over the many decades, and recently, including commercial NeuroPixel, there's the submicron CMOS silicon probes, and also Neuralink is an Elon Musk company, and accessing brain activities. They're using polymers. I can touch that a little bit later, but concept is similar. This is all lineage of the Michigan probes. I just want to point out the one thing here is a Utah probe. There's another approach in Utah, which is for clinical applications, and this probe has been implanted in the human being. But human application requires longevity and the reliability. So their structure, their shape never changed for the last 30 more years. They're still using the same thing. While the Michigan probe has been evolved into many generations and scale it up to 1,000 number of recording channels. So the topic of today is integrating optical stimulation capability onto the Michigan probes. So to recap, this is the listening part, listening of the brain, and electrically, what we call electrophysiology, and from EEG, ECOG to the beat brain implantable silicon probes. And as you get into this, and then you can access to the single neural activities rather than only the ensemble of larger number of neural activities. However, the number of neurons that you can access increased over time exponentially. And it doubled every 7 years. This is, which is called neuroscience Moore's law. Electronic Moore's law is double every 2 years or 1.5 years. This is much slower, but this is exponential. So we will be reaching to the 1,000 channels can be simultaneously monitored in 2020s, and it will be increasing more up to maybe 100Ks or millions neurons in the future. However, still far below number of neurons that human beings and even mammals have. So still a long way to go. So, but this is the Michigan architecture, Ken conceived many decades ago, and some of you may be familiar with. This concept has not really changed much. And here we have a very small microelectrode to reduce the tissue reaction and then tissue damage, and put the recording site close to the neurons as much as we can in the target region of the brain. And these signals are small, so we outplace the amplifier as close to as possible. And then we digitize the signal, and we need to multiplex them because we cannot get the 1,000 wire coming out from the probe. So we reduce number of wires. All this digitized signal will be further processed digitally, maybe such as data compression, and will be transmitted wirelessly. So most of all the modern neural interface technology is similar to this architecture. There's a many variation of the materials, like a carbon wire or polymer probes, or some different telemetry, RF telemetry, or sound wave telemetry, or optical telemetries. But how about the stimulation side? And stimulation mostly depending on electrical stimulation, but deep brain stimulation for epilepsy, seizure, tremor patient, and Parkinson's tremor patient will be done by electrical stimulation too. But in about 15 or 20 years ago, a new technology has been introduced in the science community that changed the whole entire community a lot. That is optogenetic technology. Basically, it is gene transfer technique, which means that you modify the gene in a way that you can make the neuron responding to specific wavelengths. So you have these cells in your body too. Your retina, you can see colors because each different neuron cells are responding to different wavelengths. Not in the same way, but similarly, we can modify the neuron, target neuron, to responding to different wavelengths. So we can optically stimulating neurons. This will give a really tremendous opportunity to specify target neurons, and then we can map the brain. So electrical stimulation, and you stimulate all the neurons in the vicinity of the stimulation site unselectively. What only you can do is that you can change the magnitude of the signals. However, in this optical stimulation, you are genetically modify the target neurons only. So if these neurons are expressing channel rhodopsin on the surface, these neurons are only responding to blue light, and the other neurons are not responding, although it has the same exposure to the same stimulation light. If you're having a halo rhodopsin, then it is responding only to the yellow light, not the blue light and other wavelengths. So this is a really the amazing technology, and most people jump into that. And in the literature, Science and Nature, you may see some of these papers utilizing this optogenetic technology. However, this is what they do. They're sticking optical fiber into the brain, which means that illumination site is only one. In other words, they have all stimulation in the one spot, large exposure of the brain. When I take a look at it, when I moved to Michigan, I think we can do it better. So what I try to do actually is introduce light into the Michigan probe. That's the journey that I had. The first one that I did is actually integrating this optical fiber onto the Michigan probe. So Michigan probe, the silicon shank, same configuration, same Michigan probe, and all the recording site at the end. And then we are integrating optical waveguide. This technology has been developed in long time ago, and when the before the dot-com bubble burst. And this is a known technology. And also we can do a optical mixer, which means that mixing the two different colors into the same waveguide. And at the back end, we are integrating laser diode, that's a light source, so that we can make it completely fiberless. So the laser diode is lighting different wavelengths, and they will be connecting to this waveguide through this green lens, which will allow us a very big margin of misalignment tolerance so that to making this technology manufacturable. The light will be coming into digital end. So here we have a recording site. My students will put M here as a reflection mirror from the waveguide so that we can turn on and off the laser diode, which is blue and red. We can illuminate the distal end. So we have temporal and spatial resolution. We can switching the light electrically, not by switching the optical source. And then we can distinguish a lot of neural activities. So what we can do is this. If we are eliminating blue, we are exciting neuron. We turn on the neuron. And we are eliminating red, then we are inhibiting neuron, which means that turn off the neuron. So which means that by switching light, we can turn on and off the target neurons. So we can having a switch operation of the neural circuit. This is giving an opportunity to understand the circuit connectivity of the brain. And here is one of the things that really excite my collaborator, Euisik. He's a long-term collaborator. And one of these postdocs really make that happen. And this blue light is stimulating this pyramidal neuron, while the red one is stimulating this interneuron. They're connected together. So when you can see here, so when you increase the light intensity, more excitation, more activation to this interneuron, they will be suppressing the response of the pyramidal neuron in the blue color. That means that there is a negative control feedback from this circuit connection. So from these, the dual color in high-density optoelectrode, what we can do is that we can mapping how these neurons are being connected, positive feedback, negative feedback, and which one's connected, which neurons. However, we're still lacking in the scalability because we have to integrate the light source in the back by laser diode, and then we can relay the light through the waveguide to the distal end. So at the time, brilliant students joined my group, and he just said, why don't we integrate light source directly on the silicon probe? And this is the approach, which will be completely fiberless if we can. And there's no optical coupler. Scaling is very straightforward. And also we can make this LED very small, like a neuron size about 10 micron, then we can have a cellular resolution. So this technology is really realizable thanks to the LED technology, which made a huge progress, tremendous progress over the past many years, thanks to the LED lighting business. So architecture growth of the 3-5 compound semiconductor on silicon wafer was holy grail about 30 years ago. Now it has become a commodity. So we can purchase this wafer and grow this LED layer on top of the silicon. So we define this massive structure, LED, using GaN on silicon wafer, and then we monolithically integrating recording site together on the same shank. And the rest of the process is a micromachining, same thing as we used to do, producing Michigan probe, and etching the silicon, and making a needle structure, and making electrode. So this one is a fabricated probe here, and each one has about 17 micron wide. Your hair is about 100 microns, so thinner than your hair. And it has a 4-shank configuration. You can illuminate one LED, or you can illuminate multiple LEDs, but at any given time. So we have a 4-shank probe, and each one has 3 LEDs, and total 12 LEDs, and 32 recording sites. So this is basically LED. So we can control that. So we have a control, and we can turn on any LED at any given time, any location, and then monitoring a neural response from these recording channels, and then tease out which neurons are responding, which neurons are not responding, and really mapping how the circuit is connected in the very densely populated neuron in the hippocampus, which is doing your memory consolidation and the memory retrieve. So from this, what we can do is actually map the brain and identify the neurons, which neurons are responding, which LEDs, and how they are connected. So one of the work done by my collaborator's lab, we send it to our probes to his lab. Not probes, but actually students bring all the probes to his lab. And when he leaves Michigan, I told him, don't ever think about come back to Michigan if you don't get any working or validation of in vivo. It's a joking, but actually they did it amazing. This Basaki is amazing. I learned a lot from him. And he just identified 2 neurons in separation of 50 microns, red one and pink one. And by illuminating one LED, which is about 60 microns apart, he can only turn on these pink neurons, okay? And then illuminating other neighboring LED, he can turn on only the red neurons. So he has a single neuron, single cell resolution from this, the LED devices. That was beautiful. We encouraged. This is all good story, but there's a problem. Of course, every technology has a problem, and no technology is perfect. You can see this sinusoidal wave. That is the waveform that we apply to the LEDs. Why not pulse? If you apply the pulse, we have a lot of stimulation artifact, because we are compactly integrating LEDs and recording signals together, and we have a lot of traces mixed together and running together. It's a typical engineering 101 problem. This is the coupling effect. The stimulation signal is coupled to the recording signal, which is very, very small. So what we did is we are having some shielding layer we are using double layers, and then we can suppress the stimulation artifact, but not completely. So what we did is that we are having triple layer metal structure, completely separating recording and stimulation traces. Also, we did some other engineering work to use high density the silicon to suppress the photovoltaic effect to reduce the charge accumulated from minority carrier generation. So with that, what we could do is we can almost eliminate artifact in a way that we can record neural signals even during the transition of the LED light on and off. So by having this, and we can really shipping this probe to the neuroscience community. So at the time, we are lucky to get the NSF NeuroNext hub program. So Michigan was the hub to disseminate this technology. And then we actually sent these probes to over the 100 labs around the world. And also we translate this kind of technology to the company. At the same time, we have another program going on from the NSF. That is the NSF International Program for Advancement of Neurotechnology with international partners. We sent, it was fun, 30 students come over here at campus and at boots camp, and then they send it to our international partners in Germany, University of Freiburg and University of Hamburg, and also in Korea, Korea Institute of Science and Technology. They have a lot of fun. They came back and then share what they've learned. And here, and really the instrumental to help this happen. And also we launched our international conference of advanced technology. And here in Michigan, this is an inaugural conference, and then a lot of international partners and people come over here. And I really appreciate Anne for your help to make it possible. Without all this support, nothing would have done. So having that, then we wanted to increase, we can scale it up. So that's next. So we wanted to increase the number of LEDs, and so that we can really map the brain. And then we come up with some architecture variation of where do we locate the recording cell, where we want to locate the LEDs. But controlling more than 10 LED is daunting. It's not trivial. So we designed the circuit chip that can control from the user-friendly programming. They can turn on any target LEDs at a given time. So this is the circuit that we designed, and Mike Flynn really helped out, and we are working together and design. This is basically DA converter, digital signal coming in like a SPI bus, and then an analog LED driver, and the target LED is turned on at any given time. And the recording part is also daunting because we are simultaneously recording hundreds of channels, and power reduction is really critical because all this neural signal has a really wide dynamic range from low frequency potential and high frequency single neural activity. So single neural activity is superimposed with a large fluctuation of the local field potential. That's the ensemble of the neural activities. So what we have done is we are zoom and tracking, and then actually what is tracking the large signal variation with a very small window so that we can reduce the burden of the ADC to realize the low power operation. So with this circuit that we could integrate all this together with the high density micro LED optoelectrode, which has 128 micro LEDs and 256 recording sites. So it has a LED in the middle. This is one single shank, and a recording site showing over here, in the multiple of them. And now we can play, I say that symphony music to the brain, not the simple piano tune, so that we can listen back their response to understand how they respond and how they're mapping together. So music continues in the next generation probes. So from this, what we could do is that we can kind of mapping the neural activities. Also, we can stimulate neurons all the way from cortex to the down to the deep brain region and having the mapping things. And what we are trying to do is, and also wanted to having the left hemisphere, how they interact with the right hemisphere and global connection and local connection altogether. So these are the probe that we are currently working on with the user interface software and then shipping to the partners and then collaborators labs. And probably I can talk a little more onto this, what's next. And here still silicon is rigid. And that means the rigid body inside your brain. Brain is not static, it's a liquidic, it's a fluidic, it's a kind of jelly. So if you have your sticking the rigid probe in your brain, it continuously irritating your tissue. That's what we call tissue reaction. So if you're making this the shank flexible, then probe is moving with your brain so that tissue reaction can be mitigated. So question is, can we make it flexible and elongate our longevity? So that has been done. And basically, conceptually, we integrate LED and recording site in the same way, but removing the silicon completely and replacing dielectric with the polymer layers. That's what we did. So make it flexible on the flexible substrate. So these are the probe that we realized, very small LEDs, still neuronal size. And as you can see here, an electrode and LED, it's transparent because the substrate is made of the polymer, not the silicon material. So we're happy to see this, and then we have longevity of this the probe, and this is the recording channel responding to the LED lighting, and we just having a longevity testing. And we have happy to see we have 8 months longevity of electrophysiology and optogenetic stimulation. Still, it is far less adequate for human applications, but it's good enough for animal studies. And after having that, we are having this flexible probe, then there's another opportunity open up, which is we can stack them because they're very thin, and we can wrap around a non-planar surface. Even we can flip them so that we can have a double-sided probes. So we can extend the recording channels just simply by stacking them. And also we can wrap around the probes for high-density recording capability. So this is one of the example, and stacking 3 probes together and expanding into 128 channels. But we are integrating a dopamine sensor and temperature sensor, other modalities. So we could see all the neuronal population is responding to the dopamine concentration. And there are 3 groups of the neurons, red, blue, and green. They are responding differently to the dopamine with the different lag and different magnitude. So also we can do this, the wrapping, we call origami probes. And simply, it works well by capillary force. We can put the liquid and we dry it up from this capillary force in this small dimension, like excuse me, few hundred microns. And capillary force and surface tension is a dominant force compared to gravitational force. So you can really wrap around these flexible structures. So what we could do is we can take a look at the neurons, not only from the one side, but all these 300 degrees C or around from this axis. So all this red and blue are shown the location of neurons, their response magnitude. And these are the mapping of this and how neurons are connected in kind of 3D rather than 2D. With that, I'd like to acknowledge, I should acknowledge a lot, but I just want to highlight the couple, Ken Weiss, as Dennis mentioned. He is my advisor and mentor and colleague, and he's a pioneer of the Michigan probes. Without him, and my work has not been done. I really deeply indebted to Ken Weiss. I miss him because he couldn't make it today. And Yuri Basaki is a great neuroscientist. I learned a lot from him, not only the technology, but also the life and how to approach the science and all these other difficulties. And among all these, and these are my former and current students and researchers, they did all the work, and they should get the credit. I'm just presenting on behalf of them. And the funding support, and especially I wanted to thank Kavli Foundation, which funded us under the Dream Team, and myself and Yuri Basaki, and opening the animal lab so that we can validate the technology on the same site in engineering school, and in which we have now Lopez and is a neuroscientist as a trainer and staying in my laboratory and really validating and also giving us a lot of feedback how probes should be for the next generation. And finally, Lurie Nanofabrication Facility. All the beautiful probe that I showed you today has been fabricated in the Lurie Nanofabrication Facility. I really appreciate the leadership and also the staff of your Nanofabrication Facility. And I'd like to thank you. Thank you for coming, and thank you for listening. And I just highlighted a few students who contribute the work that I presented today. Thank you.